Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. In today's lesson, we're going to talk about network flow problems. In particular, we're going to talk about the minimum cost network flow problem, and we're going to observe an example of solving this problem using the pulp package. You might have seen network flow problems in the linear programming modules. Here, we're going to treat them as integer programs and talk about the connections to the linear programming relaxations. So here's an example. So a company has two manufacturing plants and three distribution centers. And these are going to be modeled as nodes in a particular network. So it has three manufacturing plants. The plants and the distribution centers are connected by transportation channels, which are represented as arcs with directions on this network. The production amount and the demand at each node is shown. So here, in this particular example, the two manufacturing plants are node 1 and node 2. And they produce 300 units and 1,200 units, respectively. And then there are these demand locations or distribution centers, 4, 5, and 3. And distribution center 4 has a demand of 500 units, 200 units, and so on. And each transportation channel has two numbers associated with it. One of them is the cost per unit to transport one unit from node 1 to node 2. For example, in this example, this would be $12. And it also has a capacity on the maximum number of units that you can transport from one node to the other along this channel. So the goal is, for this optimization problem, is to find out the cheapest way to move units from plants to the distribution centers. So one way to think about this particular example is that these nodes, we have supplies. Right? So we have 300 units of supply, 1,200 units of supplies. And then at these nodes, we have demands, 500 units, 200 units, and 800 units. Notice that the supply is equal to demand. The total supply is 1,500 units. The total demand is also 1,500 units. So the goal is to, how do I match the supply and demand by moving stuff across these arcs so that we obey the capacities, the transportation capacities, and we also minimize cost. So here is the formulation of this problem. So in this particular problem, the decision variables are going to be the amount of the number of units that are moved along each of these transportation channels. So notice that there are, how many arcs are there? So we have 1, 2, 3, 4, 5, 6, 7. There are 7 arcs. And so we have 7 different decision variables. So x12 represents the amount that is moved from 1 to 2 along this transportation channel. x23 represents the amount that is moved from here to here along this transportation channel. And continuing, x53, for example, tells you the amount that is moved from node 5 to node 3 along this transportation channel. So these are my decision variables, and these decision variables are non-negative, and they have capacities on them, right? So for example, x53, we have a capacity of 1,000 units. So x53 is a number between 0 and 1,000. Okay, so these are the capacity constraints. On top of that, we also have to have what are known as flow balance constraints. So in particular, if we look at a particular node, let's pick this node. Let's pick this node. So a flow balance constraint tells us that, if I pick this node, that whatever comes in must leave. So what comes into this node? So at node 5, you have x45 coming in, x25 coming in. This should be equal to x53 and 200 units. So another way of writing this thing is this. So x53 plus 200 units is equals to x25 plus x45. This is just written in this form where we are always going to write whatever leaves node 5 minus whatever enters node 5. So remember, this is whatever leaves node 5, whatever enters node 5 is equal to the supply at node 5. So notice that in this particular case, node 5 has a demand, so therefore there is a negative number. So again, let me just write this expression. It says total entering flow minus leaving flow should be equal to supply. Right? That's what this means. So I should revise that. Sorry. In this case, I'm saying, so leaving flow, right? So this is what leaves node 5 minus entering flow. It's the opposite of what I just said. Entering flow should be equal to supply. So unless this is our format, it doesn't matter if we could just multiply this by -1, we'd get the previous expression. So let's look at another node just to kind of make sure we understand this. So let's look at node 2. At node 2, what is the leaving flow? Well, x23 leaves, so that's x23, plus x24 leaves, that's x24, plus x25 leaves, that's x25, minus what enters? x12 enters, that's minus x12, is equal to the supply, right? So leaving should be equal to supply plus enter. If this is not a supply node but is a demand node, this supply should be a negative number. Okay, so let's now write down a formulation of this model using Python, or let's code up this example using the pulp modeling language. We have talked about pulp in a previous lesson, so remember that you need to install pulp as well as the GLPK solver before running this code. We're going to import pulp as P, this module pulp P as a module shorthand P. First job is to create the model. This is going to be a minimized model, and so that's the term that I use, p.lp.minimize. This is a pulp parameter which tells us that the model is a minimization model. Then we introduce, we write down our decision variables. So there are these 7 decision variables corresponding to the flows on these 7 different arcs. So we're going to call x12 is an LP variable which is going to be called x12. Its bounds are between 0 and 1,000. Remember that so x12 is between 0 and 1,000. That's what the next 2 terms are. And it is a continuous variable. And so we introduce all these 7 variables. That's the first term. And then we're going to add the objectives and the constraints one at a time. So the first thing that we add in the pulp model is the objective function. So what is the objective function? It is the cost of the flow on each of these arcs summed up. So x12 unit cost is 12 units, 12 times x12, plus 10 times x14. x14 has a unit cost of 10. 15 times x23, and so on. And then we add these flow balance constraints, which says that if you look at node 1, remember that everything that leaves node 1 minus everything that enters node 1 is equal to the supply. Everything that leaves node 1 is x12 plus x14. There's nothing that is entering node 1 is equal to the supply at node 1. And so we have these 5 constraints corresponding to the 5 different nodes. This is exactly similar to the mathematical formulation that I showed in the previous slide. And once this model has been created, we just simply call the solve routine. And then we print out the values of the variables, calling each variable at a time and setting its name equal to its value. And once we do that, here is the output. So it tells us that x12 is 100 units, x14 is 200 units, and so on. And I've written out here on this graph, I've written out the solutions. And if you look at the solutions, and you'll see that all of these variables, the solutions, they obey the capacity constraints and they satisfy the flow balance constraints. So let's verify that. So let's look at this particular node 2. And so now I have 100 units and 1,200 units that is entering this node 2. That's a total of 1,300 units. And what is leaving? 900, 100, plus 300, which is again a 1,300 units. So I have a 0 balance at this node. Whatever enters must leave, right? So that's because that is ensured by the constraints of this model. Okay, so in general, a minimum cost network flow problem that we have just described, we are given a directed network. A network consists of a set of nodes and a set of arcs. And each node has an associated supply. So these are the right-hand side that I just showed in the previous example. If the supply is non-negative, this is called a supply node. If this is negative, then it is called a demand node. And we're going to assume that the network is balanced. That means that the total supply is equal to total demand. If I sum up over all of the right-hand sides of the nodes, they should equal to 0. Each arc has an associated cost, Cij, and a capacity, Uij. A flow on this network is a set of values on these arcs that obey the capacities and satisfy the flow conservation at the nodes. And the goal is to find out a flow of minimum cost. So here is the formulation. We introduce variables xij, where ij is an arc. For every arc, there is a variable. This variable has a lower bound of 0, and the upper bound is a capacity on the arc. We'd like to minimize the total flow cost. Remember that xij is the flow times the cost. We sum up over all the arcs. That's the total flow cost, subject to the flow balance constraints. What is the flow balance constraints? Remember that we look at every node we look at all the arcs, all the total flow that leaves that node. So we look at all the arcs that start at I and go to j, right? So there's a leaving minus all the arcs that enter that node I, ji, so starting at j and entering at I, is equals to the supply at that node. This is the flow balance constraint. So this is an example of a minimum cost network flow problem. So here are some characteristics. You can verify that the constraint matrix of this problem has a +1 and a -1 in every column. So if there is one column corresponding to every arc, and in every arc there is the constraint matrix has a +1 and a -1, and all the other entries are 0. This kind of a matrix is known as a network matrix. Now, if the supply data, Bi, which are the right-hand sides of this problem, these right-hand sides, and the capacities are integers, then it turns out that every extreme point or a basic feasible solution will have integer entries. So therefore, a network flow problem with integrality requirements can be solved as a linear program. In other words, we get an integer solution for free. If we can just solve the LP, we get an integer solution. So this is an important class of an integer program that are easy. Next, we will see that some integer programs which are related to these network flow problems can be converted into network flow problems and hence can be solved easily. So let's talk about what is known as the shortest path problem. This is a very important problem where we are given a graph where we have a node set and an arc set, and we have a special node called S and a destination node T. And each arc has a length Cij. Our goal is to find out the shortest path from S to T. So let me draw some picture. So here is a node S, here is a node T, and there could be other nodes, right? So these are stuff that we can visit on the way, and so on. And each arc has a length associated with it, right? So it has a length associated with it, and this is called Cij. So our goal is to find out what is the shortest way for path, for example, by which we can go from S to T. So how do we formulate this problem? So one way to formulate this problem is to say, we introduce a variable xij, which is a 0,1 variable, which says that whether we decide to traverse this arc or not, right? And then we say that, okay, when we traverse, these arcs, this solution must satisfy the following requirements. So if we leave this node I, and minus the arcs that enter node I, their difference should be equals to 0 unless we are the start node or the end node. If you're the start node, there has to be at least one arc leaving node I. If you're the end node, there has to be at least one arc entering node I. Actually, exactly one arc. So this is the flow balance constraints. So this, as you can see, this is an exact example of a network flow problem. So we can just forget about the integrality requirements and relax it to be a continuous variable. This is a linear program, and once we solve it, we are able to solve the shortest path problem. Here's another example. So we are given a set of P workers and Q tasks, and let's assume that there are more workers than tasks. Each worker I charges Cij to complete task J. Each worker can be assigned to at most one task. That's what this constraint tells us. And each task has to be assigned to a worker. Find the minimum cost assignment of worker to task. So we're going to introduce variable xij, which tells us that whether we're going to assign worker I to task j. And we'd like to minimize the cost of assignment. And these are the constraints that tells us that worker I, so at most, each worker can be assigned at most one task, and each task has to be assigned. How do we model this as a network flow problem? So first of all, we can introduce nodes where each node, for each worker, and we can introduce nodes corresponding to each task. And then we add these arcs, which tells us, so each worker has a supply of 1. Each demand node or the task node has a demand of 1. We're going to introduce a slack node, this 0 node, which has a demand of P minus Q. Remember that P could be bigger than Q. So I might need to assign, there might be some workers that are not assigned to any tasks. So all of those will be moved to the slack node. Now there is an arc from worker I to task j. So there is an arc, and the capacity of 1 and a cost of Cij. And there is an arc from each worker node to the slack node with a capacity of 1 and a cost of 0. So once this problem is, this is now an example of a minimum cost flow problem. Again, because we can relax the fact that Xij needs to be 0 or 1 because this is a network flow problem, and once we solve it, we are going to find a minimum cost assignment. Okay, let's summarize. Network flow problems are an easy class of integer programs, and various important class of integer programs can be converted to network flow problems, which we can solve as linear programs and get integer solutions for free. That concludes this lesson. See you in the next one.